Welcome again to the new class, and we'll start from the previous lecture where we were doing the Lagrangian example for this projectile motion. And if you remember that we have already calculated the Lagrangian for that projectile motion, and this was come out to be that Lagrangian was T minus V, and then the kinetic energy, if you remember, was this was half m r dot square plus r square theta dot square, okay, because the Lagrangian was that. And then we have the kinetic energy, that is potential energy, that was mgr sine theta. Okay, so that was the Lagrangian with this kinetic energy and the potential energy we have written for this projectile motion, which was going along the gravity. You have x and y axis, and then along at any instant of time, that is going to have the x and the y component here, and then this is the angle theta. So with that you write down whatever your y-axis and z-axis. This is say y, and this is say x. Okay, and then because the generalized coordinate in this case are r and theta, because r is varying wherever the projectile is there with respect to that, the r is varying, and then corresponding theta is also varying. The generalized coordinate in this case, generalized coordinates are two in numbers, that is one is r and the second was theta. Okay, so this we have already discussed, and then we have calculated the two Lagrange equation of motion corresponding to r and corresponding to theta. That was d dt of delta L by delta r dot minus delta L by delta r equal to 0. This was one, and then the second was d dt of delta L by delta theta dot and delta L by delta theta equal to 0. So we have calculated these two Lagrange equation of motion, and they come out to be this one I figured out that in the last lecture this equation of motion I did some mistake because inputting the value of dl by dr theta, but this was was okay, and this the Lagrange equation corresponding to this was twice m r dot theta dot plus this was m r square theta double dot plus gr cos theta 0. This was the Lagrangian equation of motion corresponding to this theta generalized coordinate. So now let us try to calculate this one, because in the previous lecture I had did some mistake while putting the value of delta r by del L by del r dot. So now if we calculate del L by del r dot from my this Lagrangian, this is because I had to see this value, this is going to be m r dot, and then I had to calculate delta L by delta r, that is one will come from this, that is going to be m r theta dot square, and the second component will be from this potential energy, because r is here also, so this is going to be minus mg sine theta. Okay, so now I had to take this d dt of delta L by delta r dot, and this is going to be d dt of m r dot. So there in the earlier previous lecture I did mistake that in place of this m r dot I have used this m r theta double dot there, so the equation of motion there is wrong, so please correct it down. So this is now going to be m r double dot, and then Lagrange equation of motion corresponding to r coordinate is going to be this m r double dot, and then with this negative sign, del L by del R. So I have del L by del R here. So this is going to be minus m r theta dot square, and this is going to be plus mg sine theta is equal to 0. So if I take r m common, so this is going to be m r theta dot square plus g sine theta is equal to 0. So this is my second equation of motion, Lagrangian equation of motion, corresponding to this theta coordinate, and this one we have corresponding to r, and this one corresponding to this theta. So this is the Lagrangian equations of motion in plane polar coordinate. If you calculate it in Cartesian coordinates, and then if you compare them, then you will see one interesting thing, that if we move to in Cartesian coordinates, so then in Cartesian coordinate system, what you're going to have is T equal to the kinetic energy will be half m, because this is mass of the particle. It's going to have this x coordinate and as the y coordinate here. So this is going to be x dot square plus y dot square. This is the kinetic energy, and then the potential energy will be, because this is along height h, y is varying, so this is going to be minus m, or this is plus mgy, because the reference point is here, this is 0 0, so it's coming, it's not in the negative direction of phi, it is in positive direction of phi, so this is plus mgy. So now the Lagrangian for in Cartesian coordinate system is half m x dot square plus y dot square, and this is going to be mgy. So let's try to calculate this from this Lagrangian, because now my two coordinates are x and q2 is y, which are independent. There is no constant between these two coordinates x and y, as in case of this r and theta, they were independent. So similarly we have the two coordinates x and y are independent. So if you remember that when we are doing about the degrees of freedom and generalized coordinates, so you see that degree of freedom is 2 here, but the generalized coordinate is not unique. Generalized coordinate here in this case is xy. Generalized coordinate in this frame is going to be r and theta. So now let us calculate this equation of motion for this projectile in Cartesian system. So the first equation of motion will be, this will be d dt of delta L by delta x dot, okay, and then this is delta minus delta L by delta x is going to be 0. So if you find this delta L by delta x dot from this Lagrangian, so I have x dot here, so x dot is here only, so what I'm going to get is this term, that is this delta L by delta x dot is going to be mx dot from here, okay, from here. And this, because there is this term, because there is no x dependence in the Lagrangian, so this term is going to be delta L by delta x is going to be 0. So now if you put this, so now I have to take this time dependent d dt of this thing, that is going to be, if I take d dt of this delta L by delta x dot, this is going to be d dt of mx double dot is going to be 0. Okay, so now you see that this is d dt of mx double dot is equal to 0. So what do I mean by that? This is no, this is not double dot, this is x dot. Okay, so this is not double dot, this is x dot, because this is my x dot. So so when you write it, this is x dot is equal to 0. So this means that mx double dot is going to be 0. So this is what, this is mass, and this is an acceleration. So if you see the projectile motion, the important aspect of the projectile motion is that when a particle is in motion, then its vertical motion is vertical motion. This vertical component of the velocity and the horizontal component of the velocity are totally independent. So this horizontal velocity is completely independent as compared to the vertical velocity, because this velocity is gradually getting reduced by the g, because of the g gravitational factor. So that's why as is going to the height, so this velocity remains same, but this velocity keeps on decreasing, and finally it's zero here, and then after this point it comes under the gravity. This is we already know. So this fact is, now you can see from here that this acceleration is acceleration in x direction is 0. So that means if you integrate it, this is going to be that means x dot this means x double dot is 0. That means d2x by dt square is equal to 0. If I integrate it, if I integrating it, so what I'm going to get is dx by dt is equal to some constant c1, and this is my x dot equal to c1. So this means that the velocity is constant. So that means the velocity in the horizontal direction is constant. So velocity is constant, so no force is acting. Okay, so while it is moving in horizontal direction, there is no force is acting on this. Only force which is acting is in the vertical direction, which is the gravitational force. So this is what I have. Further, if I integrate it, so this is going to be dx if I integrate it, and so this is going to be some c1 dt. So then you get this is c1t plus some c2. So now I can find c1 and c2 based on some initial constant. Now let's the second equation, which is the y component of that. This is d dt of delta L by delta y dot and minus delta L by delta y is equal to 0. So my Lagrangian is, if you see, my Lagrangian is half mx dot square y dot square minus m dy. So this is Lagrangian is half m x dot square y dot square minus mgy. So if I calculate from here delta L by delta y dot, so this is going to be from here, so this is m y dot, and this is and delta L by delta y is from here, this is going to be minus mg. Okay, so now the equation of motion from here, from this equation I've put these values. So what I'm going to get is, this is d dt of my dot and minus plus mg equal to 0, or I get my double dot equal to minus mg, or say y double dot is equal to minus g. So you see that this equation is that the acceleration is the gravitational acceleration in the negative direction. Y double dot is the acceleration in the y direction. So when the projectile is going, no force is acting on this direction, only force is acting is in the direction which is minus g. You can see from this expression. So if you further integrate it, what I'm going to get is this y dot equal to minus gt plus some constant of integration, and then if I further integrate it, this is going to dy. So this is minus gt dt plus this c1 dt. So this y is, it depends upon time, is minus half gt square plus this is c1t plus some c2. Okay, so this is my expression for y component, and this is my expression for the x component. So if I put the initial condition for, say my initial condition is initial conditions are, so at t equal to 0, so I have this velocity, say velocity is equal to 0, because when I launch, the initial velocity at t equal to 0, and then this height or say let's start from this and say this x and y is also 0, because when you start from here this is 0 0. So if I put this into say in this y at time t equal to 0, y is 0, so this is 0 minus half into 0 plus c1 into 0 plus c2. So this gives you that c2 is 0. So now your y becomes yt is minus half dt square plus c1t. Okay, so with one condition what you have is c1t. Now when you put the condition of velocity here itself here in this one, so c1 is also 0. When you put at t equal to 0, from when you put at t equal to 0, velocity is also 0, so this is going to be 0 0 plus c1. So this gives you c1 is also 0. So finally what you get is your get is y, this is yt is minus half gt square. So because c2 is 0, and c1 is also 0, so this is simply, this term remains here. So yt is equal to minus half gt square, because you know that in only the force is acting on this direction. And in the same way you can see that if the same boundary condition if you apply, then what you get is like x equal to, because when you put here xt is c1t plus c2, this c1t plus c2. So if you put the condition that x is 0 at t equal to 0, so x is 0 and at t equal to 0, the 0 plus c2, this gives you c2 equal to 0. So now you have xt, your xt is c1t, and then if you put the condition on the velocity, this is going to be constant, x dot is c1. Okay, so that is x dot t is c1. So you have two equations here for this, and the one equation which is for y. So this gives you the velocity is constant, the velocity is constant, and then this gives you that the force which is acting on is only the gravitational, because of the gravity, and this is giving you that the height, which is minus half gt square. And now if you compare the equations of motion which you get in the Cartesian coordinate with the equations of motion in you see here in polar coordinate, these equations of motion are quite complicated, you know, but in Cartesian system you get a very easygoing equation, so you can see clearly what is the dynamics. So it is not always there that what space you are working is always going to give you a meaningful simple equation. So you have to better choose that in which system you have to calculate your Lagrangian, and you have to calculate your Lagrange equation of motion. So but it has to be in terms of the coordinates which are independent to each other. Okay, I think it is clear now. Now let's move to a second example, which is I think let me have some different example, that is say example of say Atwood machine. Okay, so this is this Atwood machine is nothing but I have if I have a pulley, so if I have a pulley, and then I have a rope going over it, and then I have a mass attached to this. Sorry, my drawing is not very good. So and then if you say this is x length, and the total length of this is going to be say so this is L, so this is going to be L minus x. Okay, so this is frictionless pulley, and the length of the rope is total length is L, so this side is this one is m1 mass and this is m2 mass. So if I had to write the Lagrangian for this system, this is my Atwood machine, I have to write the Lagrangian for the system, so then I had to have this the kinetic energy for this is going to be half for this m1 mass, this x coordinate is there, so this is going to be x dot square, okay, and then for this mass m2, so this is going to be m2, L is its coordinate is L minus x, so this is going to be this square. So if I can write it, half f1 x dot square plus half m2, if because L is constant, length is constant, so it's not going to affected by the time, only the x is going to affected by the sign, so I can safely write it as x dot square. So this is going to be half m1 plus m2 x dot square. So this is my kinetic energy, so this is my kinetic energy, okay, and I can write the potential energy. This potential energy here is going to be for m1, the potential energy, because it is at height h, and this is my x-axis, and this is my reference point, so I'm coming down from the y-axis reference point, so this is going to be m1 g x, and because of v1, and then v2 is minus m2 g L minus x. So this is my potential energy. So I can write the Lagrangian here now. This is T minus V. So this is going to be half m1 plus m2 x dot square, and then this is plus m1gx plus m2g L minus x. So this is my Lagrangian, okay. This is my Lagrangian for this Atwood machine. Now, because the generalized coordinate is here only one, generalized coordinate is only one, which is x, which is independent, and it is sufficient to give me the configuration of the system where this mass m1 is located and where this mass m2 is located. So now I have my Euler-Lagrange equation. This is going to be one generalized coordinate to one Euler-Lagrange equation. This is going to be dx minus delta L by delta x is going to be 0. Now I find this delta L by delta x dot from here. This is going to be, this is m1 plus m2 x dot, and then I can find delta L by delta x because I want this thing. So this is going to be this is m1g and plus m2g, and but because this is x is minus, so this is going to be not positive, this is going to be minus m2g, okay. So this is nothing but m1 minus m2 times g, okay. So now I can put this into this equation of Lagrange equation. So that is going to be d dt of this is my m1 plus m2 x dot, and this is going to be minus m1 minus m2 g, this is equal to 0. So this is my m1 plus m2, and d dt of x dot is my x double dot, you know, and this is going to be m1 minus m2 g. So I can find this x double dot is m1 minus m2 divided by m1 plus m2 times g. So this is my equations of motion for this Atwood machine, which is giving the acceleration of the whole system, that is mass m1 and m2. If one is going up, the second will go down. So if you try to see this Atwood machine concept in the Newtonian mechanics, let's try to see whether I am going to get this equation or not. So for example, if I say you that this is mass m1, this m1g force is acting down, so there is a tension here, and then this m2 will be here, and there will be a tension force here. So there may be two cases. One is m1 is going up, or the second is m1 is going down. Okay, so if m1 is going up, if this m1 is going up, so that means this t is more than m1g. So I can write this equation, that is t minus m1g, and what is the acceleration of this is m1. So when this m1 is going up, so the tension force is more as compared to the m1g. So t minus m1g, t is a force, this force minus this force is the acceleration is in upward direction. And similarly, if m2 is going down, so this m2g which is acting on this is more than the tension force. So for this I can write this m2g minus t is going to be m2a. So because the tension is same, so I can equate these equations. So I have this t equal to, from here I have t equal to m1 a plus m1g, and from here I can write this t equal to m2g plus minus m2a. So if I equate these two, equating these two, I have m1a plus m1g is m2g minus m2a, or I can have this m1a, this I can take this side, so this is m2a, and this is going to be m2g minus m1a, or this is going to be m1 plus m2a is minus m1 minus m2g, or I can write this acceleration as minus m1 minus m2 divided by m1 plus m2g. So now you can compare that x1, that x double dot was, this was m1 minus m2 divided by m1 plus m2 times g here. Okay, here. So you can see from the Newtonian dynamics, if you equate this, you're getting the same equations. So this is for the case when m1 is going up, m2 is going down. So if you do m1 is going down and m1 is going up, so you'll get rid of this negative sign, and then you'll get exactly the same expression for the acceleration. So you see, whether you're doing the Lagrangian dynamics or the Newtonian dynamics, the final equation of motion is going to be not same, structurally same, but the dynamics which it is going to give you is same. Equation of motions are going to be same. So it is for your ease or mathematical calculation that you use either Newtonian or Lagrangian mechanics. But mind it that most complicated system which are going to be under certain constraint, or if you don't know the constraint, Lagrangian dynamics are going to be the most significant method to use to solve the mechanical problems. So I think I'll stop here, and in the next class we will continue with more examples. So for now, thank you very much.